Hey y'all, I'm back for another episode of Energy Option C in your IB Chemistry adventure. So tonight we're going to talk about the carbon footprint. IB wants you to be able to know the definition of it, why it's important, and how to calculate it. Be patient with me tonight because my tablet is no longer working, so I will be using inserting Microsoft equation to kind of help you through the math part. So if you totally get lost, let me know and send me a text or an email, and I will try to work it out on paper and then send you a picture of it. But I'll go ahead and say thank you for putting up with my tablet and keyboard. Alright, so a carbon footprint. We all know that as we live and breathe and eat and enjoy life, we are doing things that can emit greenhouse gases. The one greenhouse gas that we're going to take a look at tonight will be CO2. So if you look at the screen, carbon footprint, there are a few things that you need to know. The first thing that is what I just mentioned. It's the total amount of greenhouse gas that we produce doing things that we know will produce CO2, and then other things that are produced indirectly. It's measured in the equivalent ton of CO2. It is produced during the combustion of fossil fuels, and I'm going to go ahead and make a note here that this would be like natural gas, oil, and coal. If you remember, those are the three main types of fossil fuel. And then the final thing is that you can calculate the mass of CO2 using stoichiometry. And then once you do that for every type of fuel, you can compare which fuel gives you the least carbon footprint. And so we'll do one of those examples using coal and wood so that you get an idea of how to do that. So let's try this calculation here, calculating the carbon footprint. Determine the mass of CO2 in kilograms emitted into the atmosphere by the complete combustion of octane, C8H18, to produce, and this should be 1.00 times 10 to the 6 kilojoules of energy. All right, so the first thing that we need to do is write that balance equation. So we've got C8H18 plus, you've got your O2. I'm going to omit states of matter just to keep it easy for me. CO2 and water. We need to balance it. And the funny thing is about balancing, IB will allow you to balance an equation using a fraction. And you guys know me, that is not my cup of tea. I like it to be, oh, what happened to my number here? I like it to be, okay, let me try this again. A round whole number. There we go. All right, you guys, you may have to deal with a subscript that is not really subscript. Okay, so I'm going to go ahead and balance this equation for you using the IB style. If you do not like using fractions, I'll show you how you can get around that. Or you may remember from class that you can simply double everything, and then that will get the fraction out of the problem. So if we were to double 12.5 here, that would give us 25, and then 1 goes to 2. Isn't that interesting? Come on, big 2. Okie dokie. Let's come here. Okay, so we're going to leave that like that. This is going to drive me crazy. 16, and then 18 will be here. And then if you count all of your atoms now, you'll see that they're all fine. All right. So now we know that we produce this much energy right here. So we're going to take that and we're going to think, how much energy do I get out of this combustion? Well, the problem will either give you the enthalpy of combustion, or you can look it up. So the delta H, let's insert a symbol here. There we go. Of combustion for octane is, let me look at my notes here, 5470 kilojoules per mole. I'll do the fancy -1 here. Wow, it does not like subscripts at all. Alright, we won't do that then. Per mole. Now this is helpful because this gives you a starting point. What you're going to do now is you're going to take this energy here and this energy here, and you're going to kind of put them into a T-chart so that they're going to cancel out the kilojoules. Let me make sure that I've told you everything that's in this problem. I have. So this was given. By the way, let me write this down. This is given information. So now let's go ahead and insert an equation here that we can work with. I'm going to do this one here. And before we do that, we're going to go here and put in our 6. Okay. Now think of this as a T-chart. This is going to be your kilojoules, right? And we know that we have a -4570 kilojoules per mole. So your 1 mole is going to go on top here. So then those units cancel out. This is going to leave you with moles, and I've already calculated this for you. This is 183 moles of C8H18. So now we can go to grams. Okay. So we're going to go to grams of CO2. If you notice here that this is grams of octane, but if we come back up to the equation, we can use our mole ratios. This is a 2, and then to CO2 would be a 16, or you could say a 1:8. So we're going to come back here. Let's insert another equation here. So ahead of it, I'm going to copy this, and so if it let me put it there. Okay, waiting on my computer. Wonderful. Ah, it did it. Okay. So now we know we've got 2 moles of your C8H18, and you've got 16 moles of your CO2. So now that's going to cancel this, cancels with the bottom here. It won't let me highlight just the bottom, but oh, there it went. I think you saw that. So this is going to be, let's see, what did I get? That's really multiplying by 8, 1.46 times 10 to the 3rd moles of CO2. We can put this in scientific notation here. Insert your equation, and let's go here, here. Don't you love me talking myself through this? I had no idea that I would try to do this without my writing tablet, but you'll do anything to get information across to IB students so that you can do as well as you possibly can. So we've got moles here. We're almost done. What are we going to do now? You can probably guess we're going to go to grams. So this is your copy, and then you can go paste, and then we'll insert this little guy here to help us go to 1 mole of CO2, and then this is 44 point, you guys, I don't remember that decimal, so hold on. It's got to be at maybe 0.02 or 0.01. I'm going to go with 0.01. I am so sorry if you're calculating this with me and you don't see, you see a different number there. And then we're going to go again. We're going to do that again, and we're going to go to, because that's grams, and they want it in kilogram. Let me come up here and put my unit, grams of CO2. So then here will be 1,000 grams of CO2, and up here would be 1 kilogram of CO2. And then this will give you 64.3 kilograms of CO2. Okay, wow. Let's make this a different color so this stands out for you. We've just calculated the carbon footprint for this combustion reaction, and I have to tell you that calculating the carbon footprint is actually a longer process than I'm showing you. This is just an estimate of what it would be. It's not the exact number, and that was something new that I learned because I thought it was the exact number. But after some reading, it's just a really good educated guess. Okay, so this is how you would calculate the carbon footprint here. So what I'm going to do is I'm going to stop this video here because I'm getting close to 15 minutes, and I like to keep them under 15 minutes. I'll come back with another video and show you how to do this again using 2 different fuels, wood and coal, and then we'll compare which one has the smallest footprint. So thanks so much for bearing with me, and I hope that you have been able to learn something from this video. See you soon.